Right. So welcome everyone. Thank you for joining us for the DeFord Lecture Series. My name is Elizabeth Catlos and I'm a faculty member in the Department of Geological Sciences at the University of Texas at Austin. We are part of the Jackson School of Geosciences, and the DeFord Lecture Series is our departmental seminar series. It's been a requirement and tradition for all graduate students since the late 1940s. The lecture series is named after Professor Roland DeFord, who joined the university as a professor in 1948 with the purpose of enhancing the quality of our graduate program. The lecture series is supported by a range of endowments, and today's speaker is the Judd H. and Cynthia Walling Centennial Lecturer in Petroleum Geology. The series was established in 1983 to bring exceptional and distinguished lecturers to the Jackson School for the benefit of the geosciences community. The endowments honor Mr. Judd H. Walling of Houston, Texas. He's a 1942 geology graduate of the University of Texas at Austin and former vice president and general manager of Getty Oil Company's Southern Exploration and Production Division. He was a director and executive committee member of the Oklahoma Petroleum Council and a member of both the Western and Oil and Gas Association and the Illinois Oil and Gas Association. The lectureship was established to meet the then critical need for funding of outside speakers. Mr. Walling was instrumental in securing the Getty Oil Company chair, the first company-sponsored chair within the Geology Foundation, and it's currently held by Dr. Mark Cluse within the Department of Geological Sciences. Our speaker today will be introduced formally by Dr. Peter Flemings, who is a professor in the Department of Geological Sciences and also holds the Barrow Centennial Chair in Mineral Resources. Yeah. Oh, you have to unmute.
The first error, I apologize. I'm really pleased to introduce today's speaker, Dr. Christopher Walker. Chris graduated in 2001 from Oxford with both an undergraduate and a master's degree. And then he crossed the pond and joined Lamont Doherty of Columbia University, where he received first a master's and then his PhD in 2008, broadly in the field of structural geology. His thesis was entitled A Gravity Slide Origin for the Mormon Peak Detachment, and it was published in both Geology and the Journal of Geology. Chris went on and has 14 years of energy industry experience, broadly as a structural geology specialist. And 9 of those years were spent as part of the Mad Dog field, one of BP's biggest Gulf of Mexico assets. And he did everything from geomechanics to salt restoration to participating in a major build out at Mad Dog as they expanded that field. He's also had long ties to the University of Texas through interactions with both the AGL and the Geofluids Industrial Associates, and he has bent over backwards to get data from the industry to academia so that students can pursue their research, and we're deeply appreciative of that. Today, Chris is the subsurface lead in BP's applied science team, evaluating and developing commercial carbon capture. And Chris, I don't know, a couple of years ago, he and I were talking, and he really made probably an interesting and fairly dramatic decision to step from the exploration and production side to the storage side because he felt it was really important. And I'm looking forward to hearing what he has to say today. Thanks, Chris.
Thanks a lot, Peter. It's good to be here. Thanks for inviting me, and thanks for everyone for taking time out of your busy day to come hear me speak. I'm gonna try and share my screen. So let's see if we can make the second technical error of the day. And that should have worked.
That's good, Chris.
Okay, excellent. Yeah, and it's interesting to say, yeah, I've been definitely privileged to have, long connections with UT since I started at BP 15 years ago. And I think that does speak to, those changing connections do speak to a little bit of the theme of the talk, which is, how geoscientists can participate in the energy transition. Like Peter says, when I started at BP 14 years ago, I was very interested in salt tectonics. And so I was interacting with the AGL at UT to think about, how salt deforms. And then I got more interested in sort of pressure and stresses as they develop around salt bodies. And so then was interacting with Peter's group and the UT Geofluids. And then 2 years ago, I moved into this role, looking at carbon capture, use, and storage. And so now when I come up to the University of Texas, I check in at the Gulf Coast Carbon Center, which is run out of the BEG. And that's a really great research institution that's really been doing some cutting edge research on the deployment of carbon capture, use, and storage across Texas, across the US, and globally. So definitely really appreciate the role that UT has played, certainly in my career so far. So I'd like to talk to you today about the importance of geoscientists through the energy transition. And as Peter said, my role specifically now is as the subsurface lead, helping to develop carbon capture, use, and storage projects for BP across the US. So I'll talk to you a little bit about that, about the value we see in that, the importance we see in that, and the role for geoscientists as we develop these projects in the future, and the importance that geoscientists can contribute to this new energy transition that we're moving into, and the quest for net zero. So I always like to lead with the summary, and the summary is that geoscientists will be needed to drive the energy transition and will be very important in meeting the needs of the population of the Earth, to provide them with energy to fuel the development that we've seen over the last centuries. So understanding the subsurface will be key to delivering both the low carbon oil and gas that will still be needed even in a net zero future, the geothermal energy that is one of the lowest carbon forms of energy out there, offshore wind, where any shallow water offshore wind development will need a good understanding of the subsurface in order to create the engineered structures to harness the power of the wind. And then what I want to spend most of the time on is talking about geological carbon storage. And so geological carbon storage will require a lot of geoscientists to help with the exploration, appraisal, development, injection, and then monitoring of underground carbon storage facilities to ensure that we can develop this technology to allow it to contribute at scale and help to deliver a net zero world. And then finally, one of the things that I wanted to talk about was maybe something that we tend to overlook a little bit in our geoscience careers. And that's all the things that we do that's not necessarily associated with geoscience, but it's all the skills that we learn along the way. So we learn how to work in small teams. BP has a big focus right now on agile delivery. So small independent technical specialists coming together for the sake of a project, delivering that project rapidly at speed, and then the team breaking apart and then the members going on to do other things. Again, I think this works well with, or this translates well to how we operate as geoscientists, lending our skills to integrate across disciplines and to interact and understand what the key points from other disciplines are, incorporating that into our research and then moving forward. The other key things that we learn then are these digital tools that we pick up along the way, how to code, how to handle large data sets. And certainly as we move into the future of energy, I think this data analysis and the incorporation of machine learning and artificial intelligence will really help us to contribute not just to the geoscience data sets that are collected, but to all the other science data sets. We live in a world of the Internet of Things and lots of sensors and lots of data being collected. And I think that, the geoscientists do retain those important skills, or do develop those important skills of how to sift through that data, separate the signal from the noise, and then generate the correct conclusions from that signal in order to allow us to move forward. And certainly as BP repositions ourselves as an integrated energy company, those kind of skills will be key to delivering these integrated energy solutions to allow the company to compete in the global marketplace and to allow us to serve our customers better. So that's the highlights. You can go home now if you want, or start happy hour early. But if you'll indulge me, we can delve into these points in more detail. So hopefully I don't need to tell this audience, but we all know that global CO2 concentrations are rising in the atmosphere. And we know that that's due to human activities. And so if you look at the Keeling curve, atmospheric CO2 concentrations are now, I believe, over 410 parts per million in the atmosphere due to human activities. And these increases in CO2 concentrations have caused a rise in global temperature, with the 10 hottest years on record all occurring since 1998. So this is the reason why the countries of the world came together to sign the Paris Agreement in order to globally try to limit the amount of carbon that we put in the atmosphere. So if we view this as a carbon budget, like on this graph, which shows the amount of carbon dioxide emitted since 1876, and the surface temperature rise that those carbon dioxide emissions have changed, have created, you can start to see where we are on this graph, where our present day carbon emissions have created surface temperature rise over 1 degree centigrade above the pre-industrial baseline. And our colleagues have told us that by the time we start getting temperature rises above 2 degrees, that's when the worst impacts of global warming will start to be realized. And so that means that basically we have about another 1 trillion tons of carbon budget left that the atmosphere could take before we get into realizing the worst of those impacts. And the Paris goals that the nations of the world signed on to commit us to trying to stay well below those 2 degrees. So that means even less carbon dioxide then can be put into the atmosphere to avoid triggering these worst impacts of climate change. So the question is then, how do we continue to develop as a country, as a globe? How can we continue to raise standards of living across the world and continue to provide the energy that people need to pull themselves out of poverty and into the growing global middle class, while limiting the carbon impact of that associated energy and of that associated wealth? So that's the challenge that the world faces today, and I'm sure you're all very familiar with it. BP's approach to that challenge has been to align ourselves with the Paris goals. And so back in February this year, we made a big announcement that we set out this ambition to become a net zero company by 2050 or sooner. And to allow us to deliver that ambition, we set out a number of aims, which are listed here on the slide, and I won't go into in detail. But the first 3 of these aims are specifically around limiting the amount of carbon dioxide that we put into the atmosphere. So getting to net zero carbon dioxide from our operations. And currently that's about 50 million tons of CO2 that specifically comes from the facilities and wellbores that we have the operational equity stake in. Aim 2 is to get to net zero oil and gas, net zero on our oil and gas operations, and that's larger, sorry, on our oil and gas production. So that's larger than just our operations, and that takes us up to about 350, 360 million tons of CO2 that we will aim to reduce to zero by 2050. And then aim 3 is halving the intensity of our operations. So every barrel of oil that we produce, every cubic feet of gas, and every megajoule of electricity that we sell has a certain carbon intensity, a certain amount of carbon that was released to generate that energy. And so one of the metrics that people use then is lowering the carbon intensity of the energy that we produce. And at BP, we've set that target of halving this intensity. And so I think the latest numbers in our financial report suggested that that aim 3 covers about a gigaton of CO2. And so we'd like to reduce that by half by 2050. And we believe that these then align our company goals with the Paris goals to allow us to aim for net zero. So in August this year, then, we laid out a bit more detail on how we're going to do this, how we're going to transition to an integrated energy company by 2030. So helping to shrink that time horizon and show those more concrete steps of how we deliver net zero by 2050. And a lot of these were kind of worrying to the geoscientists inside the company. We talked about how we're going to reduce our oil and gas production by over 40%, and how we're going to stop exploration in new countries. And so, you know, a lot of the folks that I work with have specialized in new country entry and exploring in basins where no one has ever drilled before. And so it was really powerful to hear the company come out and say, well, we're not going to do any more of that. And you know, we set a lot of other targets in terms of growing our renewables portfolio and increasing our investments in low carbon energy to 5 billion a year. So a tenfold increase in what we spend today. Increasing our investments in biofuels, increasing the electric car charging points, things like that. While at the same time reducing our operational emissions and then reducing our the emissions associated with our production. So again, a lot of things that seem to imply that we might be moving away from the importance of geoscience. So the question is then, yeah, what does this mean for geoscientists, both inside the company and, you know, as a broader discipline in the world? These are the building blocks we've laid out to help deliver our purpose. And I think there's three things here that I would draw your attention to. Number one is this part of our building blocks to allow us to deliver net zero will still be reliant and focused hydrocarbons. So if you look at most of the energy outlooks that have been produced by the various global organizations that try to forecast the future of energy, like the International Energy Agency and so on, they still talk about that even in a net zero world, the world will still need a lot of hydrocarbons. The growth of renewables will not be fast enough to displace oil and gas completely from the market. And the cheapest way to deliver net zero will still revolve around using hydrocarbons, but lowering the carbon intensity and reducing the impact of those hydrocarbons. And you know, I think key to that challenge is obviously the intermittency of renewables that we know a lot about. The wind turbines and solar panels only produce electricity when the wind blows and when the sun shines. So outside of those times, you either need to have something to store the energy that's produced. So you need to either overbuild your system and then store the energy to make up for those times, or you can rely on hydrocarbons and, you know, burning natural gas for power, like we do a lot in Texas, for example, to supplement the wind energy that comes from all the wind farms in West Texas. So even in this net zero world, we still will be producing 1.5 million barrels per day of hydrocarbons. And because of the law of natural decline in hydrocarbon fields, that means we'll still have to discover a lot of new hydrocarbons, and we'll still have to manage the decline in our current fields and learn how to operate them and learn how to operate them more efficiently and with a lower carbon footprint. So there still will be a role for what you might call traditional geoscience, but a lot of it will be focused on doing things more efficiently and getting more out of the reserves that we already have. The other thing I would draw your attention to then is the low carbon electricity and energy piece over here. And this is where geoscientists can contribute in developing these new low carbon forms of energy. So again, we talked a little bit about offshore wind and all the geotechnical work that needs to be done in order to efficiently site those wind farms offshore, in the shallow offshore, the ones that at least are rooted to the seabed. We need to understand what the seabed looks like. We need to map it. We need to test the geomechanical properties. We need to make sure that the pressure variations are such that the wind turbines are going to fall over when the wind starts blowing hard. So there's a lot of geoscience work that goes into that. And then obviously investments in geothermal. So and expanding beyond the traditional geothermal of just finding places where the water is naturally hotter in porous and permeable reservoirs, and moving into what they call next generation geothermal, where we can drill down into the crystalline basement and pump water down there and then connect it through fracture systems and then bring that hot water back up to the surface, which then expands the geographic footprint of where geothermal energy can be economically competitive with other forms of energy. And obviously there's a lot of geoscience work that will have to go into that, to engineering those wells, to identifying where those where the available resources are in the subsurface, and then of mapping those fracture distributions and making sure that we can efficiently circulate water through without causing any unintended impacts to overlying freshwater systems or inducing seismicity and things like that. And then finally, where I've moved into is this carbon capture, use and storage, CCUS. So being able to efficiently remove carbon dioxide from our processes before it gets into the atmosphere, and storing it underground and making sure that it never returns to the atmosphere, but still is able to provide the energy to the consumer. And then finally, the other bit I wanted to highlight were these digital skills. So everything that we do then is going to be driven in this new company, in this new integrated energy company, through digital tools, digital skills, and innovation. So being able to deliver these solutions to our customers at the lowest cost and most efficiently. And I think it's some of these skills that we tend to overlook in our geoscience careers. We don't realize that while we're processing our earthquake data, we're also learning how to code and learning how to deal with large data sets and filtering out noise and things like that. And so I think those those skills then can then be key to the role of geoscience in the future. And obviously the skills that we use in multidisciplinary work. So understanding what is important from other disciplines, what they're telling us that we need to incorporate in our own work, and then be able to run with that and use it to deliver a solution to the problem that we're facing. So those, I think, are the key roles for geoscientists through the energy transition. And then what I'd like to talk to you more about then is my own specialty, which is carbon capture, use, and storage. And so I think the first question to answer maybe is why CCUS? What does an integrated energy company like BP see in carbon capture, use, and storage? And so I'd like to point out to this graph, which was developed by the International Energy Agency back in 2015. And this shows the CO2 emissions on this axis against time on this axis in the past, and then projected into the future if basically nothing happens. If we keep on our current trajectory, even with the announced policies that countries have put together, CO2 emissions continue to rise. And where the IEA says we need to get to in order to deliver net zero is what they call the sustainable development scenario, which is this black line. And so the difference between the red line and the black line then has to be taken up by various technologies. And each of these technologies can deliver a slice of the emission reductions that are needed to deliver net zero. So there's no one magic bullet. Instead, it's sort of an all of the above kind of strategy. And so you can see here the various technologies that have to be deployed, and the various amounts of each technology that you deploy changes in each scenario that different organizations run. But these seem to be pretty good averages. That there's a lot of gains to be made through energy efficiency. There's a lot of gains to be made by developing renewable electricity, switching from coal to gas, to expanding our nuclear power. But also you see there's a large section of a large wedge of this emission reductions that can be best delivered by CCUS. Sometimes folks refer to this as the hard to decarbonize industries. So these are some of the essentials of modern life, like carbon and steel, that generate a lot of CO2 in their production, and that can't really be replaced by renewable energy. And so here the most cost-effective solution is to capture the CO2 that's associated with those process emissions, and then either use that CO2 for something else or store it in such a way that it is permanently separated from going back into the atmosphere. And so this is why these energy outlooks tend to say that CCUS is one of the best ways to develop net zero at the lowest cost to society. However, you'll see that this wedge of CCUS starts off very small, where we are at the present day, and then grows a lot to provide that at-scale solution in the time scale that we needed. And so some of the numbers here, it's basically orders of magnitude growth are needed from what we're storing in the ground today to what we need to be storing just to make this sort of 9 or 10% number of the emission reductions that are needed. And I think that speaks to the strength of this all of the above strategy. So what is CCUS? And I'm glad we got to this 25 minutes into the talk. But carbon capture, use, and storage is a suite of technologies that can be deployed to prevent carbon dioxide from being emitted to the atmosphere. So basically, any of the feedstocks that we use in modern life tend to contain carbon. We run them through a series of industrial processes that generate energy or other useful products, and then have carbon dioxide as a byproduct. And so CCUS then involves capturing that carbon dioxide to make sure it doesn't get into the atmosphere, transporting it generally to somewhere where it can be either stored and used, and then storing it or using it. And so some of the typical methods then of transport are either road, rail, ship, or pipeline. Some of the typical methods of storage are injection into deep saline formations or depleted oil and gas fields, which can be either onshore or offshore. And some of the uses for CO2 then can be as a working fluid in enhanced oil recovery, enhanced gas recovery, or as a feedstock to other processes where it can displace higher carbon intensity feedstocks. However, present day, we see that utilization really isn't a very large component of the CCUS value chain. We don't think it will be able to scale up to meet some of those numbers that we showed in the last slide to deliver net zero. And so we think that there's a large prize to be had then by storage. That's where a lot of the CO2 will have to go that gets captured. In terms of this overall CCUS value chain, a lot of the cost comes in this capture side. So these industrial processes tend to produce carbon dioxide at a variety of different volumes, different pressures, different temperatures, and different concentrations. And a lot of the cost then is in stripping out the carbon dioxide from the other flue gases. So there are certain industries that produce purer streams of CO2 that have a lower cost of capture. And so when we talk about CCUS deployment in a few minutes, those are the industries then that will sort of float to the top, that will focus on and that's natural gas processing, ethanol fermentation, and ammonia and hydrogen production. That's where the pure streams of CO2 tend to come from. And so that's where it's going to be most economically efficient present day with the incentives that are available to deploy CCUS. And then as we look to the future, as things like carbon taxes and carbon offsets start to really enter into the conversation, specifically as countries seek to meet their nationally determined contribution limits under the Paris Agreement, that's when I think we'll start to see this incentivization of capture from the cement industry, the steel industry, power generation, and even the atmosphere. So there are some projects that are being announced right now of folks looking to deploy direct air capture. So literally sucking CO2 out of the air and storing it underground. But again, as concentrated as CO2 is in the atmosphere, it's still only 0.004%. Whereas in natural gas processing, the CO2 concentration could be 100%. So again, this is sort of aligned here in cost order. So globally, the CCUS industry looks something like this. There's an organization called the Global CCUS Institute that tracks all the deployed projects across the world. And this map helps you to visualize where they are. There are only 19 large-scale facilities in operation present day, and the majority of those are concentrated in the United States, and the majority of those are using the CO2 for enhanced oil recovery. And a lot of that speaks to basically where the incentives are right now. Without any sort of carbon tax, it's generally cheaper to merely emit the CO2 into the atmosphere. And so most of the places where there is revenue attached to that CO2 is where it can be used for hydrocarbon production. However, the US has recently made some changes to the tax code where there is now an incentive for capturing CO2 and storing it underground. And so we're starting to see a lot more of these projects come through the pipeline in the US. So I think the color scheme here shows the red projects are closest to completion and the blue projects are still under development. But you see there's a lot of projects being kicked off in the US right now to start trying to capture some of these tax credits. And that support from the government is really helping to grow the CCUS industry at scale in the US. Europe is also doing pretty well in terms of incentivizing CCUS. But you'll see that the bubbles are smaller and the bubbles here relate to the scale of CO2 captured. So they have a couple of large government-funded projects and then a series of smaller demonstration projects. However, the language that the EU is putting into their version of the Green New Deal to help some of the coronavirus recovery efforts I think will start to incentivize a lot more CCUS projects in the EU. And so that will help them to start developing at scale as well. And then finally, you also notice a concentration over here in China and Japan. And so China, obviously the world's largest CO2 emitter, recently announced a goal to try to get to net zero by 2060. And it has been active in the CCUS space, certainly in the pilot stage and in the development stage. It only has one active project in operation right now, but I think we'll start to see that really take off in the coming years as China gets serious about trying to reduce the amount of emissions it puts into the atmosphere. So when we think about growing the CCUS industry, the obvious question is, can we? What is that potential for global growth? And I think, this graph or this map shows it pretty well. That pretty much everywhere across the globe where there is a sedimentary basin, there is prospectivity to store CO2. Basically, we're just simply looking for reservoir seal pairs. So porous rock overlain by impermeable rock. And that exists in many of the sedimentary basins across the world. And to meet some of those IEA targets of how big will CO2 storage need to be, you can get to numbers around 90 or 100 gigatons of CO2. And if you add up all the storage that we think is available globally, even at the low end of that estimate, we're down at 1,000 gigatons of CO2. So we only need to fill up 10% of the potential pore space that's available in order to meet, in order to allow CCUS to contribute at scale. And obviously, even if this low end turns out to be wrong and the high end is more like how much CO2 storage resource there is, then obviously it's a lot less than 10%. So we think there is a lot of potential for growth for CCUS. We think that there's a lot of need for CCUS. And certainly focusing in now in the US, CCUS is a commercial opportunity today. So the National Petroleum Council last year put out a really good study on CCUS deployment in the USA. And if you're interested, I suggest that you go to this website, dualchallenge.mpc.org, and you can download multiple volumes of their recommendations for how to speed up the development of CCUS across the country. But there's lots of great detail in there about what are the lowest costs of capture, which industries make sense to deploy CCUS on now, and how you develop a CCUS project. So some of the strengths that the US has are these high concentrations of CO2, short distances, so good geology, short distances to sinks and low transport costs through existing pipeline networks, and current tax incentives at the state and federal level. And so if you can string together a project where your costs are less than your incentives, then you can start to think about actually developing these projects today. And there is a lot of activity and a lot of interest underway. And I think if you set up a Google search or read the news, you'll see it seems like every day there's a new project announced in the US. And so that's one of the reasons why BP is interested in it. And if you zoom out to the scale of the whole US to think where these projects might happen, I think this graph, this map is a pretty good one. It comes from the Department of Energy Carbon Storage Atlas, which is another good reference if you're interested in reading more about this. But each of these dots is an emission source across the US, scaled by the amount of CO2 that they put out and colored by the kinds of industries that puts out that CO2. And then the blue polygons are the existing sedimentary basins where CO2 storage will most likely work. So you can see there's a variety of different emission sources across the country, with a lot of refining, which is the pink color, concentrated down here on the Gulf Coast. A lot of oil and gas, which is the blue color, kind of scattered around the sedimentary basins. A lot of ethanol, which is these red colors throughout the Corn Belt. And then a lot of electricity generation, which are the big green dots, pretty much everywhere. So you'll see that many different regions of the country have the potential to develop these CCUS projects. And the skinny blue lines here are existing CO2 pipelines that mostly move natural CO2 around the country for enhanced oil recovery purposes, but in the future could be used to also move captured anthropogenic CO2 to start linking emission sources with sink destinations. So in the US, we emit about 3 gigatons per year of CO2 from over 6,000 stationary sources, but we also have a large storage potential. So enough to store our own emissions for over 500 years at current levels. And then we have the expectation that emissions will continue to fall in the future. So we really think that CCUS can contribute to helping the US get to net zero as well. So what does the CCUS project look like? This is another schematic from the Global Carbon Capture Storage Institute. And basically, on some level, it looks very much like an oil and gas development, but in reverse. It's capturing the CO2 at a facility and it's injecting it underground in a deep well into a porous formation and having it be trapped down there by an impermeable formation. And so that can either be into a non-hydrocarbon bearing reservoir that's where the only thing that's in the pore space is oil and gas, and so you is water, and so you can displace that water and fill it up with CO2 instead. Or it might be in a reservoir that once held oil and gas. So you can replace that pore space, replace that pore volume with CO2, or you can use the CO2 as a working fluid to help extract more oil and gas, but with a lower carbon intensity, and then capture the oil, capture any CO2 that comes with it at the surface, and then re-inject it back underground in a closed loop to help to get to low carbon and maybe even carbon negative oil. Which is some of the work that has come out of the Gulf Coast Carbon Center at UT, actually, looking at the carbon intensity of some of these CO2 EOR fields and suggesting ways to help them to lower their carbon intensity, to use more CO2 in the production, and therefore to deliver carbon neutral or even carbon negative oil. And because you're all geoscientists, I don't need to tell you that the Earth doesn't have these giant caves underground that are filled with oil. Instead, if we look at a hand specimen, we're looking to store the CO2 in the pore space between all the grains of rock. So this is sort of the picture to have in your mind when you think about CO2 storage. And geoscience is going to be essential then to developing these CCUS projects. We have to guarantee that our carbon storage complexes, so the reservoir seal pair that is going to hold the CO2, we have to guarantee that it will provide safe, secure, reliable, and permanent storage of CO2. And so that means a lot of geoscience work needs to be done up front to ensure that the site we're investigating has the capacity, the containment, the injectivity, and the monitorability for the CO2 in the future. So once we inject the CO2 underground, we have to do continuous monitoring and data collection and processing to make sure it's behaving as expected, to make sure that it's not pressuring up a formation where we don't want it to pressure up, or moving through a fault or a legacy wellbore and getting into a zone where we don't want the CO2. And then even after the project has been completed, there's generally a long period of what we call post-injection site care. So monitoring of that CO2 plume to demonstrate that it is stabilized and to enable the responsibility for that CO2 to be handed back to the regulator to remove that liability from the individual corporation. And so those monitoring periods can range from 50 years to 100 years. So that's a lot of geoscience work that has to be done then to ensure that CO2 stays where it is. And if we think about this in terms of the traditional sort of exploration workflows, this is an example of something that we refer to as an exploration triangle that kind of shows all the geoscience work you need to do at a basin level in order to focus down on the prospective plays for hydrocarbon, narrow that down to leads, to prospects, and then finally get something that's drill ready. All that same work has to be done for geological carbon storage, with the additional things that need to be done to make sure that the CO2 can be monitored after it's injected, to make sure that it's not going to leak through pre-existing well bores, and to make sure that we have the rights to store the CO2 in the formations that we're looking at. So in the next couple of slides, I'll just give you a taste of some of the work that we do to assess the capacity, containment, injectivity, and monitorability, to show you how geoscientists can contribute. So for capacity, we look at different trap types, which might be simple structural and stratigraphic closures, where we can do the equations to calculate how much pore space there is available to store CO2. We might look at depleted oil and gas fields, where we can think about how much oil and gas has been extracted, and then calculate that to a mass of CO2 and then think about injecting that CO2 back underground. Or we might get into something that's a bit less familiar to us, which is migration-assisted storage, where we're looking for gently dipping cap rocks, and then we inject the CO2, we let it travel a certain distance underground, and then we allow the hydrodynamics of the reservoir system to arrest the movement of that CO2 and to stabilize the plume over time. And again, the Gulf Coast Carbon Center at UT has developed a really good software program called EasyTool that helps you quickly run these dynamic simulations. It's so simple that even a geologist can do it, is what my reservoir engineers tell me, but they still won't let me touch it. For containment, we are at first looking at structural and stratigraphic traps, but over time, some of that CO2 will get left behind in the pore space, some will dissolve in the water, and some will react with the existing minerals so that the storage security gets more secure over time. And so this is a little schematic then of what this might look like, with a row of injectors down dip, putting CO2 in the ground, and then that mobile CO2 gas cap slowly making its way up the natural dip. Some of it gets left behind in the pore space, some of it dissolves in the water, and over time the hydrodynamics of the system stabilize that CO2 in a predictable way to ensure that it never comes back to the atmosphere. And I know I had trouble visualizing this when I first started, so I really like this visualization that was put together by Chris McMinn at the University of Oxford. And I realized that sharing video over Zoom is generally a bad idea. But hopefully you can see this representing effectively the CO2 gas plume and the aquifer, and the gas plume will spread out and move up this very gently dipping slope. And as it does so, it runs into hydraulic resistance from the water, and it begins to dissolve into that water. When the CO2 dissolves in the water, it creates a CO2 saturated brine, which is heavier than the water, which then sinks. And so as it sinks down, it then becomes less likely to rise up and less likely to escape, and ensure that it becomes permanently separated from the atmosphere. Injectivity, again, is very standard geoscience data collection and processing to develop dynamic models of how the CO2 will behave underground to make sure that our wells are able to inject the CO2 at the rates that we need it to in order to create a commercially viable project. And here are some examples then in cross-section of how that CO2 might spread out, and in 3 dimensions of what the reservoir simulator might look like of that CO2 plume as it's generated underground in the reservoir and then trapped by the sealing intervals. And finally, monitoring. And this is, again, something that I had to struggle to get my head around, but there's a lot of different technologies that can be deployed in order to track the CO2 underground and make sure it's staying where we want it to stay. So this is an example from the only current active saline storage project in the US, which is in Decatur, Illinois. And this is led by the Illinois State Geologic Survey at the University of Illinois, Urbana-Champaign. And this aerial photograph shows all the different technologies that they deployed in this demonstration project to help them find out which ones are the best ones for tracking the CO2 underground. So in cross-section, they have an injection well in blue that goes down into the reservoir. They have a monitoring well in purple, so that they can track how that CO2 plume spreads in the reservoir away from the wellbore. And then they have a shallow monitoring well, seen here in green, that also has a bunch of geophysical sensors to listen for microseismic events, which helps them track where the pressure where the pressure wave of the CO2 is spreading out. And then they also have a bunch of shallow soil gas monitoring wells, shallow aquifer monitoring wells to make sure that the drinking water reservoirs are not being pressured up, or we're not seeing any impacts from the CO2 injection. And then finally, they also have INSAR reflectors to see if there's any deformation of the ground surface, GPS stations to see if there's any lateral deformation of the ground surface, and then a whole series of soil and air monitoring systems as well. So as you can imagine, that creates a very large amount of data. And I think, there's a big role there for geoscientists in sorting through that data, understanding what the signal looks like compared to the noise. And specifically, if we think about this in the long term, if there is a risk that develops, it's probably not going to develop on day one. So that's going to be, creating those tools and those artificial systems that can process that data and that can recognize what a dangerous signal looks like or what a deviation from background looks like, in order to realize and be able to intervene when we detect something going wrong. So that concludes everything I wanted to share with you guys. But just in summary, again, I think hopefully I showed you that there are lots of roles for geoscientists and that we will be key to driving various elements of the energy transition. We'll still need to understand a lot about the subsurface to deliver low carbon forms of energy to meet the demands of the world. Specifically, geologic carbon storage will require a lot of the traditional hydrocarbon exploration, appraisal, development, injection skills, and then some new skills around monitoring as we seek to make sure that, that CCUS can be done safely and reliably and at scale to deliver a net zero world. And finally, I would just encourage you not to overlook the other skills that you pick up along the way. So the working together as teams, helping to deliver agile projects, and picking up all those digital skills and learning the data science and data analytical tools that will be transferable, so that one day you can start off interpreting geophysical signals for a deep water reservoir, and the next day you're learning how to maximize offshore wind deployment by studying how quickly turbines move. So with that, thank you. And
yeah, thank you so much. We really should end it here. We really appreciate you coming and discussing this topic with us. And I hope to see everyone here next Thursday, but I'm going to end the meeting now. Thank you so much, Dr. Walker and Peter, for hosting, moderating, and I'm going to end it here.
Thank you, everybody.
Thanks a lot.